we have been studying magnetic models, exchange interactions and models that lead to long range magnetic order, and we found out that there is this celebrated model called Heisenberg model, which is typically H equal to minus J Si dot Sj, where Si and Sj are the corresponding quantum mechanical operators for spin s moments, and you sum over Ij. You can make it I greater than j, so that you just sum only once each point, but nevertheless this is the model. Typically you can also have a magnetic field in the system. So, that magnetic field is couples to the system, and this is G mu b H dot Si. This term can represents that. Generally one absorbs this G mu b and everything into H and writes a model which is just H dot Si, and then sum over all S for a constant magnetic field H in a particular direction. So, that means if the H is in the z direction, this will just become H sigma S z sum over all sides. So, as we said before that Jij positive and negative give rise to different kinds of states. Jij positive will give you a ferromagnet, whereas Jij negative will try to misalign the spins, align them antiferromagnetically. But if there is a field, of course, the field will try to align it in its own direction. So, that will be a competition between the field and the J. If the J is antiferromagnetic, for example, then there will be a competition. If J is a ferromagnetic interaction, then of course, if you put the field in the same direction, then there is the field chooses the direction, and then the ferromagnet has no competition with the magnetic field, because all spins will align in that direction and satisfy this J. Okay. So, typically as I said before that this I and J are chosen to be nearest neighbor, because the interaction drops off as you go to further and further neighbors in your lattice, in your solid, and then you can write a Heisenberg model with only nearest neighbor interaction. That means Jij equal to J only for I and J nearest neighbor equal to 0 otherwise. So, that is the way it works, and that is that's called the nearest neighbor Heisenberg model. So, this Hamiltonian represents a nearest neighbor Heisenberg Hamiltonian. This half you can ignore, you can absorb it in J. So, those are things that we will do as we go along. So, these as we have been discussing, there are these various kinds of spin orders that come from this interaction, and they provide you a long range ordered state. The long range order can be of various kinds. This is, for example, ferromagnet, this is antiferromagnet, which are also shown below, but there is a state that is mentioned here as C, which is called the spin glass, and I will come back to it. It is a different kind of state where magnetic moments are in a metastable state. There is a slow dynamics by which the moments relax. The moments are reasonably far apart from each other, and that leads to a state which is dynamic, in the sense that there is no spin freezing over a long time. So, it relaxes to very slowly to its stable state, but that relaxation time could be very large, fairly large. Okay. This is an example which I chose because you can see that this is an antiferromagnetic arrangement. Excuse me, and this is determined from, say, neutron scattering, and you can see that the in the antiferromagnetic state, the unit cell, which means the repeating units are is doubled. The size of the unit cell is double the size of the chemical unit cell. Chemically, this atom is manganese, this atom is also manganese. If you do not look at the spin, then you will your unit cell will be just this will be the distance between the lattice constant that you will use to find out your unit cell. Whereas, here for example, the unit cell has to contain more than one atom, 2 atoms, and that means the unit cell dimension has doubled, and this is extra. So, even the previous picture you can see in the antiferromagnet, the repeating magnetic structure comes by after jumping 2 units, 2 lattice constants, not 1 lattice constant. So, in this case, for example, if you had a perfectly paramagnetic state or even a ferromagnetic state, you could have chosen your unit cell with just one atom or one moment. Whereas, here in the magnetic unit cell, you have to go 2 steps to repeat the magnetic structure. That means, your magnetic unit cell is twice the original chemical unit cell. That has profound consequences in determining the state of even sometimes metallic or insulating state of a system. The way one determines if something is paramagnet or ferromagnet is, of course, one is you can do neutron scattering and then actually look at the magnetic structure locally. The other one is that you even from susceptibility, see, neutron scattering requires you to go to a reactor, not for everything you go there. If you can determine without going to a reactor, is fine. So, susceptibility, for example, tells you a lot. So, susceptibility, for example, has these different forms for ferromagnetic, for paramagnetic, ferromagnetic and antiferromagnetic systems, and this is really interesting that even at MSc laboratory measurement, where you can measure the susceptibility, you can actually determine whether something is paramagnetic, ferromagnetic or antiferromagnetic. See, the way the Curie law gets modified in a ferromagnet is that there is a C by T minus T c. So, there is this at some instead of going diverging here at T equal to 0, now you have a finite temperature where the divergence occurs. In real systems, of course, you will not find the divergence, but there will be a sharp upturn around this T c. So, the way it goes is C by T minus T c in ideal ferromagnets. In antiferromagnets, it goes as C by T plus some theta, and at high temperatures, and that above the nail temperature, and that here also this formula is valid for when you are coming from above T c. Here also you are coming from above T n, and this is the behavior that you will see. So, the other interesting thing about antiferromagnet is that, as I said, that if you put a field, suppose you have an antiferromagnet where spins are aligned this way, and now you put a magnetic field which is say in this direction. Let me write small h for magnetic field, then there is no confusion with Hamiltonian. So, this h is in the direction of these spins, and then what will happen is that these spins are now unhappy, because they are in their high energy state, they are antiparallel to the magnetic field. So, they will try to align along the direction. It is also possible that they may not the state may completely change, and there are situations where such thing can happen. It is just not that these spins all align along the magnetic field. That happens for very large magnetic field, of course, but there are other possibilities that I will not discuss here, but you can think about it. The other thing is that sometimes the system itself has a magnetic anisotropy, and so certain directions of magnetization are favored, a certain direction is favored, and in that case if the magnetic field is parallel to that direction, then the susceptibility has this behavior, the chi parallel, whereas if it is perpendicular to the sublattice magnetization, then this is called the sublattice magnetization. So, sublattice magnetization has a direction which is up here along this up direction. So, sublattice direction magnetization is calculated by taking this up spins and multiplying this down spin moment by -1, and that means you actually turn it around and make it in this direction and sum over all of them. So, that direction that is the direction about the field is here perpendicular to that, the field here is parallel to that. So, and you can see that susceptibility in the perpendicular direction to the sublattice magnetization is more or less getting flat, whereas the parallel one is coming down. Okay. At high temperature, of course, it is a higher temperature, above nail temperature, of course, this is a paramagnet. So, you will again get back there is no distinction between parallel and perpendicular. Actually, in actual practice it survives little bit, but I mean those are coming from crystalline anisotropy, magnetocrystalline anisotropy and so on. The system itself has certain directions which are favored, but let us not get into that. This is the usual picture that you will get in a good antiferromagnet. So, the parallel and perpendicular susceptibilities will be different below Tn. So, that is the message that I want you to carry for antiferromagnet. Now, there is this system, there are systems which are called frustrated antiferromagnets. Now, frustration of course is a very common term these days, and it is an English term that says that you are not satisfied, right, and it is indeed the case. So, let us take this example, and as I remember I mentioned that you have lattices which are bipartite or non-bipartite. Now, this lattice for example is a non-bipartite lattice, it is a triangular lattice. Now, what we have is that in this triangular lattice we are trying to fit in an antiferromagnet. So, my Hamiltonian is minus j Si dot Sj. So, here it is just minus j S1 S2 plus S2 S3 plus S3 S1. Okay. So, this is an equilateral triangle, all j's are same and j is greater than 0, j is less than 0. So, that you want a antiferromagnet. Okay. And then so okay, fine, let us put a spin here, and these are spins, say for example these spins have up and down quantum mechanical spins and spin half, and say up and down components only. Then this spin, this is 1, say 1, 2 and 3. So, this will also be up, this will be down because it is antiferromagnet. Now, what will happen to this one? This spin just does not know which way to orient, because if it orients up, if it is up, then this bond is satisfied, this will be happy. If it is up, then this is ferromagnet, so this bond will be unhappy, whereas this bond is happy. Okay. So, that is the situation you cannot satisfy this particular spin. Whichever way you point it, it will be frustrated, because one of the bonds will become dissatisfied. So, that is called a frustration. This happens in non-bipartite lattices with antiferromagnetic interactions with spins which are the quantum spins here, for example, with up and down components. Whereas, if you had a classical spin which can rotate in any direction, then of course, you could more or less, you could not fully satisfy the interaction, but you could lead to a compromise solution, which is this spin is here, this spin is here, this spin is here. So, they have 120-degree angle between the two, between each two. So, this is the best compromise solution you could achieve. You could not get 180-degree, but you could get 120-degree. Whereas, here you are lost, you just do not know what to do. This spin basically is it has both the states which are degenerate. So, it is a doubly degenerate state. If you put up spin, this will be dissatisfied. If you put down spin, this will be dissatisfied, and the energy is the same. So, this is a doubly degenerate state which is frustrated. Whereas, this in a classical spin, of course, you can rotate the spin in any direction, you could get this kind of a compromise solution with 120 degrees angle between the two. These are called frustrated systems. Degeneracy is an interesting thing, because once you have a degeneracy, that has a higher entropy. So, these states carry higher entropy. Then of course, I discussed ferrimagnet at some point, where you have usually two different atoms in the neighbor, and so their spins have different magnitude, their moments have different magnitude, and this alignment is kind of alignment is called a ferrimagnetic alignment. Okay, so now we have discussed a lot of phenomenology without doing any calculations. So, at some point we have to show you how to do calculations with these models, and I will just choose one celebrated model, which was written down by somebody called Ising. He wrote this model, which is very simple. You can get this model from Heisenberg model in when there is extreme anisotropy, for example. Let me just explain. So, I have this Heisenberg model minus j. Let me just stick to nearest neighbor Si dot Sj. So, this means minus j I and j nearest neighbor Si x, Sj x, these are components, x component, y component, Si y, Sj y plus Si z, Sj z. Okay. So far so good, I have done no approximation. Now, there are systems where it is possible that this j is not the same along all directions, and suppose you have a situation where j z, where one component is in one direction, j is much higher than in other directions, and that direction let us choose z, and so j z is much greater than j x and j y. This is of course an anisotropic situation. The system has this anisotropy, for example, say, and in that case, of course, I can neglect this x direction interactions along the x direction, and so see here what we have written is an isotropic, all jx, jy and jz are same, but suppose they were different, I had to write it differently, right. I had to write it as jx here, jy here and jz here. So, and then I am saying that jz is much larger than jx and jy. So, I will write this as is the Ising's model minus j si z s j z. I and j are nearest neighbor. So, this model is called the Ising model, and it has only one spin component, which is the z component. So, when one writes this model, one often just does not write this z, because it is assumed that you have only one component, and Si z takes values plus or minus 1, plus 1 or minus 1. So, so that is the model that that is for this is a celebrated model called Ising model, and we will discuss how to solve these models both approximately and exactly. This is in one dimension, of course. Approximately you can solve it in any dimension, but for that approximation, of course, is the one that I will discuss is mean field approximation, but in one dimension, one special dimension, this model can be solved exactly, and you can calculate the magnetization, the free energy, and so on, and that solution is really interesting because it tells you a lot of physics about such models. Before I go to the discussion of that solution, let me just outline the one dimensional Ising model pictorially, which is done here. This one, for example. So, you can have a situation like this. All spins are up. This is in one spatial dimension, because your spins are aligned along one direction. If I had a two dimensional model, I have to put spins here also. One thing you should realize, that the spin space and the real space where the spins are very different things. So, in spin space, the spins are quantum mechanical objects, and they have Sx, Sy, Sz components in the spin space. So, and for quantum mechanics, for spin half, for example, they follow SU2 algebra. This is real space. I can have a situation where spins have Sx, Sy, Sz all components, but the real space is one dimension. That will be Heisenberg model in one dimension. So, you should be very careful when you it is just a matter of practice. You should just remember, when we say one dimensional model, that means the space dimension is one dimensional. The space in which the spins are living, they are embedded, is the moments are embedded, the atoms are the atoms that carry these moments is one dimensional. So, so let us just consider this one dimensional model where the spins can only have two directions, or say down, spins can be down. As you can see, these two states have the same energy, can't distinguish between them in terms of the Hamiltonian, they are degenerate states. Nevertheless, let me just so this is one state which is all up, and this is one state which is all down. Both are ferromagnet, and both are both have the same energy. So, let us stick to just one dimension. So, in this case, for example, in one dimensional situation, this is my lattice, and this is the spin configuration, and this is the ground state. So, every bond now has this energy J plus J. So, every bond has this minus J energy, because the spins are parallel and they are plus 1, the spins are all plus 1. So, all bonds have the energy minus j. From the Hamiltonian you can easily see that. One question which is interesting is that what is the next excited state? Which state, for example, lies just above, just the next one above this state. See, this is infinitely extended on both sides. Okay. So, this is an infinite lattice, there is no boundary, say, or you can just put a periodic boundary condition and make it infinity again. So, nevertheless, whatever the situation, we are dealing with an Ising model with only spins can only take plus 1 and minus 1 values, and it is an infinite system. The question is, this is the ground state, of course, for we know it is clear from here, but at 0 temperature, of course, you will land up in this state. This is at least the lowest energy state, there is no doubt. Now, I want to create the first excited state of out of this, and this is something that most often what one does is that one just takes a spin and just turns it around and makes this state. This is obviously one choice of an excited state, because now these bonds are these bonds are unhappy, these two bonds have their j's are unhappy, this Hamiltonian is unhappy, the energy here is now plus j, all the others are minus j. So, if this state has energy E0, this is an infinite state, number of spins is infinity. So, this state will actually have two spins being dissatisfied, you will rise this energy by 2j. This was minus j and became plus j. So, 2 into 2j, so 4 E0 plus 4j. So, from minus j you brought it to plus j. So, each of these broken bonds, these are called broken bonds or unsatisfied bonds, will cost you 2j amount of energy, and 2 of them are broken. So, you will get this. But is this the first excited state? Is there any? So, you are saying that this is, I am saying that this is E0 and the next one is E0 plus 4j. So, is this correct? It is not true actually. Let us see what can be another state. So, let me again plot write down the spins. Now, I of course turn this spin down, but I keep all the other spins on the right down as well, and all the spins on the left up as well. This is again infinite lattice. So, now you see how many bonds are broken. There is only one bond that is broken now, this one. So, this has an energy which is E0 plus 2j. Okay. So, that means there is a state in between whose energy is E0 plus 2j. So, that is that means that this is what is shown here in this B picture on the left hand side, that instead of creating two defects, you have created two defects in the top figure, whereas in the bottom figure, see in this the way I have drawn in this figure, you have created two defects, one here, one here. Instead, I have created in the bottom figure there is only one defect. So, this state is represented in B in the left hand picture, and this is the first defect state that you can, this is one defect state, and this is the first excited state you can have over the ground state. So, that is what we will do in the next class, is we will discuss how to solve the problem of to find out the ground state, and of course also since we will solve the problem we will find out the finite temperature situation, whether that ground state survives in finite temperature or not, because there are thermal fluctuations at finite temperature, and from an exact calculation one can do that. From a mean field theory calculation one can approximately do that in any dimension. For an exact calculation we have to stick to one dimension. I will also discuss little bit of the symmetry of this model. From the symmetry you can actually guess a lot of things, and little bit of that I will do, and then carry on doing the solution and then finish Ising model.